Planning horizon and its effects on CBM system. Abstract. This study investigates a problem of machine inspection and condition monitoring, CM, for condition-based maintenance, CBM, in the Nigerian electric power industry using 1 and 2 years as planning horizons. These planning horizons were applied on a developed model and prescribed method of solution of combinatorial optimization to obtain results. A 2 years planning horizon provides a savings of 10%, 16%, and 27% respectively compared to a 1 year planning horizon for 1 month, 2 months and 3 months inspection intervals. Increasing the planning horizon has the tendency to decrease the CBM total expected cost of the system. Implementation of this strategy stage by stage can provide an optimum planning horizon for the system during its useful life. Keywords: CBM, planning horizon, maintenance scheduling, CM. Introduction. Over the decades, the Nigerian electric power industry has evolved tremendously. In recent times, it has shown the indication of moving from a regulated enterprise to a deregulated one. However, amount of electric power produced in the last 5 years has always been below 5,000 MW. With a population of over 180 million people, this amount of electricity is grossly inadequate. The promise made by various governments to provide an uninterrupted power supply of electricity to its citizens has failed. Providing 24 hours of electricity daily to Nigerians should be taken as yardstick to measure the performance of any government in Nigeria. The supply of uninterruptible electricity is a figure of merit that measures the level of development of any country. With the concerted effort put up by government in its anti-corruption war and the drive for industrialization, much is still desired to show its reflection in the amount of power available to its citizens. Many companies have closed shops and the remaining few are still struggling to survive. Proper management of the electricity industry of the country is needed. Deregulation is the key. Installation, operation, and maintenance of the facilities in this sector should be the central focus. The use of condition-based maintenance will accelerate and fasten growth in the Nigerian electric power industry. Condition-based maintenance, CBM, is an equipment maintenance procedure for detecting the condition of the equipment in order to evaluate whether it will fail during some future period and acting appropriately to avoid the consequence of that failure. 1. Maintenance is carried out when there is an obvious need which will increase the availability of the equipment in the system, as well as lower the maintenance cost. The data acquired could be used to determine whether the system is running at a normal operating condition. If the limits of the preset values are exceeded, the reason behind it can be determined and prediction made for future equipment breakdown and failure. Condition-based maintenance requires taking the result of the analysis and planning the maintenance afterwards. A structure is needed for effective utilization and communication of condition monitoring data within the establishment requires 2. Condition monitoring is important to the maintenance personnel as it allows it plan preventive work and possible serious consequences of breakdown. 3. CM has the capacity to reduce maintenance cost by 45%. 4. The typical purpose of condition monitoring is to identify potential failure with the intention to accurately schedule maintenance activities so as to prevent operational interruption. 5. These warnings are known as potential failures. 6. It is identifiable physical conditions which indicate that a functional failure is about to occur or is in the process of occurring. Akpan, et al., 2016 presented and solved a CBM problem for a system subject to inspection. The objective of this work is to investigate the effects of planning horizon on CBM total expected cost, TEC, and to present and solve a formulated combinatorial optimization problem for a 4-machine system based on 2 planning horizons of 1 and 2 years. 2. Methodology. 4 turbines in a FAM, 4, electric power station in Nigeria were used in the case study. Data were obtained from this source and elaborate discussions were made with managers, supervisors, engineers, and maintainers on CBM implementation strategy in the organization. This data was applied on a developed model and combinatorial optimization used as a method of solution. In this study an exponential distribution was assumed. 1. Where is the failure rate of the CM component in machine I? Where the actual is number of failure of machine I in a planning horizon. 2. Where the mean time to failure is given as 3. Is the uptime of machine I. The cumulative distribution function, CDF, is given as 4. For an exponential distribution. 5. The CBM model had been presented and solved by Akpan, et al., 7. 6. Where tech is the total expected cost of the system. And 7. CPT is the average cost per month. And are given below. 8. Is the depreciation cost, P is the acquisition cost, the planned years of replacement. 9. Is the inspection cost of machine I, labor cost and time to inspect machine I. 10. Is the downtime cost of machine I in interval J, is the production loss and the downtime for production loss. The failure cost is expressed as 11. Where is the repair cost, the increased cost of running the machine above alarm limit, the time interval. A combinatorial optimization technique was used as a method of solution in this research. The model formulation is: minimize the CBM cost, tech. 12. Subject to 13. And are given as in equations 8 to 11. Is an integer, is the basic cycle, is the inspection interval of machine I. Further possible combinations of are generated with multiple of, e.g. and. The unit has 4 turbines as shown in table 1 below. The planning horizons are 1 and 2 years respectively, t equals 1 year and 2 years. Table 1 shows the input data for a FAM, 4, electric power station. Table 1, input data for a FAM, 4, electric power station. Machine type, per year, N. Is CM instrument cost for the system. 3 results and discussion. Table 2 shows the total expected cost for a 1-year planning horizon for the plant. Table 3 shows the total expected cost for 2 years planning horizon for a FAM, 4, electric power station. From Table 2 and Table 3, at a FAM, 4, the total expected cost for 1 month, 2 months, and 3 months inspection interval for a 1-year planning horizon were, N11, 959,027, 478.48, and 6,603,344,243.89 and N4,833,239,016.77 Akpan et al. However, for a 2 years planning horizon, the total expected cost for 1 month, 2 months, and 3 months inspection interval are, N 22,704,831,220.60, N 12,118,536.68.73 and N 8,384,784,048.35 representing an increase of 90%, 84%, and 73% respectively. These reductions provide CBM cost savings. Table 3 shows the total expected CBM cost for various combinations at a FAM, 4, for a planning horizon of 2 years. Option 3 in Table 3 has the least total expected cost of N 8,384,784,048.35 per year, with an average cost per month of N 349,366,002.05 for 3 months inspection interval. 4 conclusions. A 2 years planning horizon provides a savings of 10%, 16%, and 27% respectively compared to a 1-year planning horizon for 1 month, 2 months and 3 months inspection intervals. Increasing the planning horizon has the tendency to decrease the CBM total expected cost of the system. Implementation of this strategy stage by stage can provide an optimum planning horizon for the system during its useful life. Further research work should be conducted for systems subject to other failure distributions like gamma and Weibull.